All right, good morning, folks. Still have a little bit of time. Just thought I'd say a couple words as I had just started the recording so that people can adjust any volumes if they need to later. Put this water over here. Maybe. Hope you had a decent weekend. Maybe you created a snow sculpture or something. Yeah, something like that. I gotta move these things. Let's. I need to put this somewhere. Okay, that'll work. The next meeting will be April 23rd. 42 seconds. I can't finish this email right now. Okay, we'll come back to that. All right, good morning. Hope you're doing okay. I'm going to try something new today. We're going to see how this goes. Um, it's Optimization is, I think, a challenging topic. So I'd like you to see a problem done through, and then I'd like you to try some problems. This is going to be kind of different, especially in this format, but I would like you to please try to play along with the process here. Just a reminder that we've got a quiz on Tuesday and Thursday. I do need to write and post those. And just as a general reminder, there is still web work, so please keep up with that. There are, I should say, actually, regarding this topic, so it won't be due for a little while, but I would encourage you to get started sooner rather than later. There are these questions in optimization take up a little bit of time. And so because of that, actually, it's quite a lot of work, but I several years ago designed a couple web worker questions on my own. Now they look long, but the original questions that are in WebWork are that long. The original questions in WebWork just give you like one answer box, and you gotta type in your answer, and it's either right or wrong, right? And that's really disheartening. And I noticed how frustrated students were with that in the past. So what I did was I was like, you know what? If there's this many steps in the process, what if I designed at least a couple questions? I mean, it takes about an hour or two to write just a single question in this format. But what if I just designed some questions where you would go through and do a step one and then step two, and you put in your answer for that part, and I mean with unlimited number of attempts, and design it so that if a certain part is right, it will go green so that you can see, oh yeah, I'm progressing the way I need to. So there are some web work questions that look rather long, is what I'm trying to point out. But the other ones, the standard web work ones in this topic are just as long. It's just they just give you one final answer box, which is a little unfortunate. Just a reminder when office hours are. Please make a visit, especially in this topic. I think there'll be a lot of questions that come up. And then finally, oh yeah, the Murphy Learning Center has online tutoring. Please drop in. They happen to be using WebEx as well, so if you've joined for class in this format or office hours, then you are good to go as far as, so not the same web address, but if you go to the Murphy Learning Center webpage, you will find uh, a link there. So first of all, the big picture where we are, we're gonna. I devoted 4 class days to optimization. So last time we had one, not last Thursday, it was technically last Wednesday, right? You get what I mean, though. The last time we had class, we were talking some geometry things to get all set up. And then Monday, Tuesday, Wednesday this week, we're going to complete this story on optimization. The general idea of what is optimization is you're trying to find X so that you have the largest of a amount of fill in the blank, whatever that thing is. It depends on the problem, or smallest amount of something. And these are extremely practical. I mean, the idea that there are numbers floating around in just about any discipline, in any field, in any sector, any business, and there are numbers that are you want to be small and numbers you want to be large is very much a part of everything that we do. It's one of the biggest uses of math in general. Um, I will just comment that the method of finding local mins and maxes, that is using the first derivative test or the second derivative test, those things will show up in their places here, as well as the method of finding absolute mins and maxes, computing the actual y values using f and not f prime. These things all have their place in this kind of grander thing that we're looking at. It's basically you've got all these tools, you've got to now see what tools are you going to apply. Most of the time, I will comment that it is usually the first or the second derivative test. As you go through the process, though, please remember that derivative is slope. I can't emphasize this enough. The more you remember that derivative is slope, the better all these things go. And then I'll say this about the problems we are looking at today, tomorrow, and Wednesday is there's so many different types of optimization problems, and at the same time, I don't want to burden you with too many. But that said, even with what we're going to see, it will seem like a lot. And sometimes I think what happens is people try to memorize their way through this problem and that problem, and I don't think that's what you should do. I think there's a big overall pattern. Like all of these have the same kind of grand steps, and then there's a lot that's problem specific that's a little different. One problem deals with surface area, and another deals with cost, and another deals with profit. And so please try to see the big picture as much as possible, and see that the big steps, like step one is, or I don't know if I even necessarily want to number the steps. What I'm saying is like you should always do this, and then you should always do that next. And those big ideas you'll see in all the problems, even if the problems look very different from each other. So try to see as much of the big pattern as possible. If we were meeting in person, I would have printed out this one pager. On one side, it would have been one PDF, on the other side, the other. So the optimization handout, it would have been kind of neat to have as a reference in front of you, but it is a handout I designed that kind of, for better or worse, and maybe worse, it lists what you need to do in sort of like 7 or 8 steps. And I think when you have many steps, you get to talk about kind of one little thing at a time in each step. But sometimes the problem with having so many steps is you kind of can lose sight of what's going on. So in the slides, what you'll see in just a moment is instead of like 8 or 9 steps or whatever it is, you're only going to see like really 4 steps. So we're going to try to compact it. So you got to kind of listen to what we're doing today, and then maybe look at that handout and see kind of which way you prefer. It's going over the same stuff. It's just a matter of how many steps do you want to call it. There's pros and cons, obviously, to each approach. And then finally, the optimization problems. I actually have this on the other screen. We are going to kind of work through as many of these as possible, or rather you are going to, and I'm going to walk around for office hours. We'll use the chat feature for that. But first of all, let's dig in. I think the best thing to do is get started. So if you were to click on that link, not that you need to right now, there is this question on that problem sheet. So let me read it aloud and then we'll get going. Menards is starting their own line of soup and wants to design a soup can which will hold 500 cubic centimeters. What dimensions for an aluminum can will use the least amount of material possible? Okay, so we're just kind of diving right into our first problem, and I'll say that all optimization problems, um, the so that we have common language that can be used from one question to the next and the next. We use this word objective to mean the thing that you're trying to make as big as possible or as small as possible. So, in general, you want to look for the superlative. So, sorry for the English grammar portion of class today, but what I mean is a word that's trying to indicate like largest or smallest. So usually the word ends in an EST. It doesn't always. In this case, our word is least, right? So sometimes you'll see words like cheapest. So cheapest is just a one-word shortening of smallest cost, right? So you're trying to always look for a thing like that. So least what? Well, least amount of material. So in this example, that least is the superlative. It lets you know that the objective is least amount of material possible. Okay, so step one, identify the quantities that are relevant in the problem. By quantities, I mean anything that would have a number associated to it. Identify the quantities and assign variables to each of the quantities. And then also note, this should just be note which quantity is the objective. Draw a picture if possible. So in this, if we just start from the beginning, let's see. So start their own line of soup. That doesn't give really any quantities yet. Hold 500 cubic centimeters. So there's a number right there. And if you look at just how the unit is written, it's a cubic centimeter. So we should be thinking volume. Then there's this question of what are the dimensions. Plural is actually correct. There are two dimensions for a can. So there's the radius of the circle on top, and then there's the height of the can. So those two will be quantities. And then finally, amount of material. That, how much metal it takes to make a can is actually the surface area, right, in a nutshell. So this amount of material is just sly wording to talk about the surface area. So those are the quantities. I've got them just here on the next slide. We've got the capital A, surface area of the can, that is the amount of aluminum, that's what this amount of material is trying to talk about. You've got the volume of the can we had set up there, and then the height and radius of the can. So those are, in this problem, the four quantities. You can always start identifying quantities, and then if like step 2 doesn't go well, often what happened is you maybe didn't notice that there was a quantity. You can always go back to step 1 and say, oh yeah, there's this quantity as well. And then draw a picture if possible. So here's what I've got for that. Right, this is, we've seen this kind of can drawing from last time we met. Okay, and then one last thing in step 1, we've got to identify which quantity is the objective. We already talked about it, least amount of material possible. So it's this A, the amount of aluminum, or the surface area. That is the thing we're trying to minimize. So in this case, our objective is to minimize A. So we've got these four quantities. Oh, by the way, I'm going to pause for a moment, give you a moment to write these four things down and point an arrow up to here to say, write minimize. So you might just, I think it's good to take notes, and you might just be staring right now, but there's a lot of things to keep track of in the next steps and so on. There isn't room on a slide to put all the pieces here, so I would write down this 500 cubic centimeters, and then write A equals surface area of can equals amount of aluminum, and write minimize. Write V equals volume of can, R equals radius of can, H equals height of can. So I'll give you a moment. Okay, step 2 is to write down equations which relate the quantities together. So there were these four quantities. They were, in our problem, they were the surface area, there was the the volume, the radius, and the height. And so then, are there any formulas, any equations that we had seen last time that relate relate these four variables together? Now, maybe not all four variables in the same equation, but there are these two equations, right? So copy down the volume of a cylindrical cylinder from last time we met, and then the surface area of a can. Just a reminder right now, why not, that this too had appeared because we were collecting like terms for the area of the circle on top and the area of the circle on bottom, so a pi r squared plus a pi r squared, whereas this too does not come from the same place at all. I just want to remind you that we actually had unraveled the label of a can, and so then that rectangle, one side of the rectangle is 2 pi r, which was the circumference of the circle, and then the other side of the rectangle was the height of the can. Okay, so we've got equations relating the quantities together, right? These are how these quantities are related. And then you need to solve, in step 3, you need to solve for the objective, and then essentially apply all of our older techniques. Before differentiating, though, you have to ensure that there's only one variable on the other side. So solve for the objective. I want you to recall that in this problem, a was the objective. Look, a is already solved for. Like, it's a by itself on one side of the equation. So we don't have to solve for anything here. Normally, in some other problems, you have to do something to both sides first. So we don't have to do anything to both sides. A is already solved for. However, before differentiating, ensure there's only one variable on the other side. You'll notice over here, pi doesn't count. Pi is a number, but there are two variables. There's an r there, and there's an h. So what we need to do is take care of this situation, right? So the problem is we want to differentiate, but we don't differentiate when on the other side, let me keep underlining that other side there, when on the other side there's more than one variable. And in this case, we've got two variables, we've got r and h. So we need to somehow get rid of a variable before differentiating. You pause. People have done this in the past in 175 in my classes. They've tried to differentiate when there's still multiple variables. So there's a problem. Our solution is to apply some algebra, substitute with any known values and variables. So look at the other equation, right? So that's we've got this. We also have this number that we didn't quite mention yet. It was just in the stated problem that the volume was 500. So if you plug in for the V, up in the volume equation, you can replace the left side, instead of with a capital V, put a 500 there instead. And look, this equation over here, where we needed to still have A solved for, has two variables r and h, but we could get rid of one of them if we substitute. And so the question becomes, look at this equation right there, and you want to ask yourself, what's going to be the easiest thing to do? Should I solve for h here, or should I solve for r here? And I think it's actually going to be easier to solve for h. The thing is, if you want to solve for r, there's an additional step where eventually to solve for r, because you see an r squared, you're going to have to square root both sides, and that's going to bring up plus and minus signs. It will be extra work. So let's solve for h. In this boxed equation, to solve for h, all these things over here are multiplied together, so we should divide both sides by pi r squared. And we'll get 500 over pi r squared is equal to h. Okay, now that we've got h is equal to this fraction, we can go back up here and replace the h that's right there with the fraction 500 over pi r squared. Why don't I pause, give you a moment to write that down here. So I want you to write a equals, and just make that one replacement, please. So we've got a equals 2 pi r squared plus 2 pi r. Here's the place to replace that h with, this is also multiplication, so you could draw a multiplication symbol or not. You recall, 500 over pi r squared, something like that. So here it is in a nicer printed version. Okay, now the fortunate thing is in what's written right here on the right of the equal sign, there's only one variable. The only variable is r. And now, I hope I've changed the phrasing from what I've used in the past to try to really emphasize this idea that before differentiating, there's a before, there's an after. So you first make sure that there's one variable on the other side, and in the underlined text over here, there is only one variable. It is r. Now we can differentiate. But let's not differentiate this as written. We could, however, look, we have a product, we'd have to use the product rule. We have a quotient, we need to use the quotient rule. Let's just do a little algebra first so that we don't have to work so hard. First of all, there's a pi in the numerator and there's a pi in the denominator. So we can cancel a pi on top and on the bottom. I wouldn't draw slashes right here actually, because when you look back at your notes it might be confusing. But if you cancel a pi on top and bottom, you can also cancel here in r on top and bottom, right? There's an r times r in the denominator. So you cancel those. Also, you've got a 2 and a 500. Those are both in the numerator, so there's no canceling, but we could simplify that as 1,000. You have something that looks like this. A is equal to 2 pi r squared plus, so that term stayed the same. The 1,000 is coming from 2 times 500. Oops, the pi should not be there. Sorry about that. So the pi is canceled. That's the saddest thing, actually, to have pi cancel. And then r in the numerator over r squared in the denominator would leave you with just a single r in the denominator. But if you have just a single r in the denominator, instead of an r to the positive first, you could write this as an r to the negative first in the numerator. So how are we doing with this? We'll pause, we'll take questions. How's a equals 2 pi r squared plus 1,000, no pi, sorry, times r to the negative first? Okay, not seeing anybody unmute a mic. I'm going to then say we've done a huge step in the process. When you get to here, you're in a very good place. Now, I want you to think about this like this is y and this is x, right? So the capital A is like if we were to graph this, get the y-axis and the x-axis. The question becomes like, what should x be, so that y is as big or as small as possible. In this case, y or a rather is the amount of aluminum, and we want to not use as much as possible. So we're trying to, in the graph, we're trying to look for a local minimum. So we have all the techniques. It's just things are not called y and x. So we should now that we've solved for the objective, we can differentiate. Let's find a max or min. So just to comment, just overall points first that we can talk about in a moment with other questions. If the input is naturally restricted to a closed and bounded interval, then you'll typically want to find an absolute max or min. This is actually rather rare. Most of the time what you have is not a closed and bounded interval. So you usually typically use the first derivative test or the second derivative test, and then you look at each critical number to see if you're getting a local max or local min. That's what usually ends up happening. So we'll look at our example. In our example, the variable on the right side, the thing that was like x, was r, and there was no restriction really given in the problem about what kind of value r could be. It didn't say that the radius can't be 1,000,000. That never was stated. But it kind of makes natural sense that the radius can't be negative, so there's this restriction here, 0 to infinity. But that's not a bounded interval, so it's not one of these, where the x value is stuck between two other fixed x values, a to b. So we're going to do this otherwise thing. We're going to look at first and second derivative test. Okay, so we'll take the a that we had earlier, which was 2 pi r squared minus, here the pi is appropriately missing, plus I think we had 1,000 r to the negative first. I believe that was a earlier. And so then we'll take a derivative, right? So think of capital A as being like y, think about r as being like x, right? So when you differentiate 2 pi r squared, power rule on the r squared, so 2r, so then the 2r times the 2 that was already there, 4 pi r minus 1,000 r to the negative second. Okay, at this point, it's kind of very usual things. I hope what you're seeing on this slide looks very familiar to things that we've done. Even if the algebra looks a little different, I hope that the process, the overall big idea, looks the same. So first of all, this r to the negative second, I find it a lot easier to think about the algebra that happens next if I rewrite r to the negative second in the numerator instead as r to the positive second in the denominator. So to have 4 pi r minus 1,000 over r squared equals 0. Why does this help me? Because, oh yeah, and we set this equal to 0, right? So you take a derivative set equal to 0, you're going to hear that story quite a lot. We've already done that quite a bit. So why does this help? It's when you have a fraction inside an equation always has an equal sign. I always find it helpful to multiply by a denominator on both sides. So I'm going to multiply both sides by r squared. All I did was I took the line above and I just wrapped each side in parentheses and wrote an r squared. On the left side, we've got to distribute r squared. So you'll have r squared times 4 pi r, and that'll end up being 4 pi r cubed. You'll also have r squared times this fraction, but the nice thing that happens when you multiply those two things together is the r squared on top and the r squared on bottom will cancel. So I don't want to cancel symbol them here. That looks a little strange to me because we've still got to take care of the r squared times 4 pi r. So it doesn't make sense to draw in any cancellation lines there. After distributing, then you should have 4 pi r cubed minus 1,000 equals, and then on the other side, 0 times whatever is just 0 anyway. Okay, so to solve for r is like our x here, right? So let's add 1,000 to both sides and divide both sides by 4 pi. So you'll have r cubed is equal to 1,000 over 4 pi. I did those two algebra steps in one step there. And then finally, to get r, we've got to undo cube. So to undo a cube, you've got to cube root both sides. And you'll have r is equal to the cube root of 1,000 over 4 pi. Okay, so that number, I mean, the algebra is all here with quite a lot of detail other than doing two algebra steps in one. But this number we're going to take with us and use in the next part of the process here. So what we need to do is, since we don't have a closed bounded interval and we're not going to do the absolute max min thing, we should take this special x value, r value, x value, and either look at the first derivative test or the second derivative test. For the first derivative test, just a reminder that you've got to look at what happens to the first derivative both before and after the special x value. Well, this x value does not look all that fun to work with. It looks like some awful decimal or something. So the second derivative test, you don't have to look before or after. You just plug in directly at that x value, or I guess this directly at this r value. So let's actually compute a second derivative, which actually doesn't look all that painful when you look at the first derivative right here was 4 pi r minus 1,000 r to the negative second. So yeah, compute based on the first derivative over here. Let's compute the second derivative. 4 pi r differentiates to 4 pi, just like 5x differentiates to 5. So number times variable should just end up with the number in front of the variable. And then another typo here. This should be a 2,000. Sorry about this. 2,000 r to the negative third. So the negative 2, right, comes in front from the power rule. Negative 2 times a negative 1,000 is a positive 2,000. So plus 2,000 r to the negative third. We're not going to set the second derivative equal to 0. That's how you'd find inflection points, right? So you've got to really keep track of what we're doing and why in this process to make it work. We're trying to right now, we took the second derivative to try to apply the second derivative test. So all we got to do is plug in this number into the second derivative. And so we'll have, again, this should have been a 2,000. But that's not, so I know this looks awful, but if you look at it, actually, once you plug in for this r, and it takes up so much space to write, that's the most confusing part about it. 4 pi is just right there. The only place to plug in r is down here. And I even, to try to avoid confusion, tried to really emphasize that there's no negatives, because it says r to the negative third. That's really an r to the third r to the positive third in the denominator. Point being, all this stuff over here, once you plugged in for r, there's no minus signs anywhere. So the number has to be positive. And so if the second derivative is positive, you have a local, think about it, if the second derivative is positive, I even put the hint here. Second derivative positive means that the graph of your original function a is going to be concave up. So you're going to have a local minimum. Right? So you have a local minimum at this x value or at this r value. We're essentially done with the process. All we need to do right now is go back and make sure we answer the original question. So based on kind of how much stuff happens, I always tend to forget what was the original question. So as a final step, step 5, I guess I should have numbered it, is to answer the question which was asked with appropriate units. So in this question, we were asked what should be the dimensions of the can. In other words, what should be the radius and the height of the can? Well, we know, first of all, a while back we had solved for h. We had solved for the height as being 500 over pi r squared. This becomes relevant again. At the time we used it to try to reduce the number of variables before differentiating, but it's going to be useful again. So the value of r from previous slide, we know that that value of r is good for making capital A small. We saw that this value of r is going to cause there to be a local minimum. So this should be the radius, right? R, recall if you go back to step 1, the list of what all the variables meant stood for the radius. So this is good, right? And we just need units. So that's what that's doing there. But then the question was about dimensions. It's really in that one wording, it's asking two things. It's asking for r and for h. Well, we have r. How do we get h? Well, that's where this comes in. We solved for h. Now we should just plug in this number r that we have right there. So it looks like this, right? So 500 was copied right there. Pi was copied right there. The square was copied right there. We just got to plug in r, and I know it just takes up a lot of space, but this right here is really 500 over pi times plug in for r, quantity squared, and then stick the units on this centimeters. Okay, so that actually in completeness answers the question, and just to complete a sentence out of it, I know it spans over 3 bullet points here, but I mean this to be a sentence, right? So using r equals that number, and the height is that number, centimeters, those will minimize the can surface area if the volume of the can has to be 500 cubic centimeters. So I'm going to pause, see if there's any questions here. I will click on this link also as this pulls up so we can look at it. Are we doing anything overall with the process here? Any step I can review? It is an involved process. I have to admit that. Like overall, it takes a lot of work to do this process. The thing is, I think when I think back to word problems, I mean, I know student attitudes for word problems are like, oh, these are painful, and I don't even know where to get started. And I get that point of view. And in a college algebra class, I hear sort of the one side is, I, when are we ever going to use this math? And then there's word problems, and then I get it though. Like those word problems in an algebra class are often there's this sort of like, well, that's not like what people would really do. I guess the mixture problems have become very relevant lately. But these the kinds of word problems that show up in calculus, you could think of those algebra ones as warm-ups, right? Because you still have to do this interpretation of what's going on. Now these questions actually deal with things that are considered rather important to people in society, but they take work because of that, right? The more realistic a problem is, I mean, these are not even. There's even more realistic if you want, but we're gonna not overdo it. Here's a picture. I had to change the scaling so that you could kind of see what's going on. So I just typed in the original A that we had, and the computer just graphed it. It didn't know that the radius was a had to always be positive. So over here, here's where r is negative, like a negative 8.63 centimeters for the radius doesn't make sense. So we should only actually pay attention to this portion of the graph, kind of over here in the first quadrant. I should do this to point to it better. And we need this point right here, but how are we going to get this? Well, beside graphing, but these numbers are decimals anyways, right? So there's that side of the thing, and the thing is, if you think that technology is going to solve all your questions for you here, it doesn't happen. There's quite a lot of algebraic and geometric reasoning that you need to do to get to this place. But the point we found was actually this one. So the value of x that was earlier, I've got this highlighted right there to give us that vertical line. It's this number. So this number right here, this 4.3 ends up being it's the radius. This 348, that's not the height though. Let's just be careful. This is the y coordinate. It's on the a axis, and a was the amount of material. So if you wanted to know what this 348 was about, it wasn't asked about in this question, but this number happens to be the actual amount of surface area. So there's other choices for the radius, like if you chose the radius to be 6.6, then the amount of surface area, the amount of aluminum needed to make that can is going to be 428 square centimeters. So the least amount of aluminum occurs down here, but you use a total of 348 square centimeters of aluminum if your radius is 4.3. So let me go back to the slides and say what's going on here. The big picture is to use either finding local or absolute, either maxes or mins. And the one real difference between what we're doing now and last week is there's lots of variables. So what you need to do is make sure you've got the objective on one side, and then on the other side of the equal sign, you need to have only one variable. And in order for that to, like, here's our example, right? There were two variables to the right of the equal sign. There was an r and an h. So we had to substitute in our case to get something that we could differentiate. And in general, to do that process of getting from like two variables here down to one variable, you've got to interpret what's going on, model, really pay attention to what your quantities are, your variables, use algebra formulas, use geometry formulas, substitute. What I'm going to ask you to do is to take class today to try questions 1 through 6. I mean, so what I want to do is say, you can leave a mic muted if you want. You can type a private comment to me, but like this, tomorrow you're going to see me demonstrate a different kind of problem that's not addressing questions 1 through 6, but I want you to try. I know this sounds strange, but this is a subject area that does not go well just watching me do a bunch of these. So give these a try. If you get stuck on a question, you can just use in the chat window, you can select my name if you don't want to type to the whole class, and then I will respond. Many of these are geometric, so draw a picture. If you get stuck and you want to show what that picture looks like, you can turn, if you have a device that does this, you could turn on the camera for a moment and point the camera at your work. see a question here. I saw a question pop up and then it went away. Okay, I can see it here. Yeah, good question. How do I write back? Like this. I see, because he chose which. That makes sense. I believe the next meeting will be there. Please share. What is... See how people are doing. Okay, just a reminder of announcements. Quiz Tuesday and Thursday. Keep current with web work. Um, and office hours are still as usual, as shown in the schedule here. And the Murphy Learning Center has drop-in tutoring. We will end the recording a little early.